Yeah. So I mean, I think this is actually these folks grew out from a request of from some of the participants to actually who would like to see a very concrete example how this integral formula works, which actually Francis explained before, but I will explain again. So the plan for these two talks is really just to go through all the details of how this equivariant localization and this Jeffrey curve type formula works in a concrete example. And this example is really some integrals or tautological integrals in the section theory of jet moduli spaces, which I explain in a second. And so it might be a little bit boring for some of you because the goal was really just to explain everything, how this works in action. But I try to keep up motivation as well. So that's the plan. Okay. So so I start with defining what this moduli space is. It's a non-reductive moduli space of jets of maps or jets of curves in an affine space, and that's modulo some non-reductive reparametrization group. And so the idea is that there is some, this is a non-reductive quotient, so we can look at the non-reductive GIT quotient and apply this integral formula to calculate some intersection numbers. And this has some nice enumerative geometry applications, roughly. So I will explain, I kind of start with the motivation and then in the second half, maybe today and tomorrow, I will really focus on the actual calculation and explain the details of the formula. Yeah, do you have any questions? No, okay. So actually, this is an example which led to the proof of the polynomial hyperbolicity conjecture. So this is also a motivation to do this. So in the end of the second talk, I hope I finish and I will show you this formula, which is a iterated residue formula for some intersection number, whose positivity actually implied the polynomial hyperbolicity conjectures of Green, Griffiths, Lang, and Kobayashi. But as I said, there are some other enumerative geometry applications as well. So let me start with what we're talking about. So this is jet moduli space. So what this is a very simple object. So I will define JK1M as to be the set of K jets of maps from, it's a complex, it's a map from C to Cn, mapping the origin to the origin. So in other words, this is just really the, if you want, this is a K-jet, so this is the set of K tuples, the first K derivatives of this map. So that all of them are just vectors in Cn. So this is basically a couple of K vectors, if you like, as a vector space. This is a very simple affine space. And what makes it interesting is that if you look at this really as a jet of maps, then of course, so you can look at this as a map from C to Cn. So if you have as an F here, you can reparameterize your source C using some polynomial reparameterization. And so what does it mean? So let's see this in some, how this action works. So diff K of 1, 1, and actually the regular part means that the same, except that so that f prime is non-zero, right? So the first derivative is non-zero. This first vector is non-zero. So this diff K11, this is just is a group as formed by jets of reparameterizations of the origin of C at the origin, but we have to take regular jets, so they form a group. And so let's work this out. So what does it mean? So if you take F in local coordinate Z is given by Z times F prime 0 plus Taylor expansion, and you take only the up to degree K, take the K jet of this. So this is your F, and your reparameterization is given by a polynomial in one variable. So it's just really just, let's say it's alpha times Z plus alpha 2Z square plus alpha K Z to the K. It's just the element here. So this means that alpha 1 is non-zero. Then the action is just this reparameterization. So we have seen this before. So if you take the composition of this at Z, it's going to be a linear action. So it's going to be given by a matrix. So this is your, so this is your original. If you take this as a base, as a basis, you take first derivative and K derivative divided by K factorial, and this is multiplied by a matrix, and that's the matrix has this form. So this is alpha 1, alpha 2, alpha K, alpha 1 square, alpha 1 to the K. So it's an upper triangular matrix group parameterized along the first row with K parameters. So and the generic, so an entry here is just sort of polynomial. So so let's say this is the IJ entry is the sum of so the ith row we have a degree I polynomials, and the weighted degree is equal to J. So I1 plus 2I2 plus, sorry, I shouldn't use I, so IJ, so let's say R1 plus 2R2 plus K, RK is equal to J, and R1 plus RK is equal to I of alpha R. It's not really important. So it's a polynomial, you know, the generic entry is a polynomial in the I, in these parameters, and that actually forms a group, and that's an interaction given by this linear algebraic group. So that's it. So what we can see that this is actually that was the action, and then this is the terminology. So my definition. So definition, if we call JK1n mod diff K. This is just as a set of orbits now. This is a anyway quasi-projective. But for now we can think of it as a set of orbits. So this is the moduli of K jets. Okay. So in other words, we take K jets of curves or maps from C to Cn. You can do the same. We will see in for manifolds as well, but up to reparameterization of the curve. Right. So yeah. So there is a fiber version of this, which is called jet bundles. So the jet bundles. So basically, this is, as I said, this is a JKX. So X is a complex manifold. Is really the set of k-jets fk from C to X modulo some equivalence relation. So two jets are considered to be equivalent if the first k derivatives are equal at in some. In other words, let's say in this way. So, and then this is the, so we say that this is an equivalent relation, which means that two jets are the same or two maps are the same if the first k derivatives are equal. So there is this is actually fibers over X. So if you take a map Fk, then you can map it to the origin. So we see that the fibers are isomorphic to JK1N. And, you know, we have to be careful here because this is, okay, so let's just say F here. So this is a map from C to X. And there's this equivalence relation which says that if two F and F prime are the same under this relation, if the first k derivatives are the same at origin. So let me, this is just like a not very rigorous definition. Let me put down the rigorous definition. So in fact, JK X is going to be really an associated bundle. It's not a vector bundle, but it's a fiber bundle. So so with fibers JK1N. So let's see what this is. So JKX is not, it's not a vector bundle. So the structure group is a non-reductive group. So what is this diff Kn? Is really just what I denoted by JKNN. The reparameterizations of Cn, polynomial reparameterization, so JK. Polynomial reparameterizations of Cn. So if you take this is a principal diff Kn bundle, diff X. So if you take the associated bundle with fiber JK1N, this is actually what it is. So, and it's as it's you know, it's not a vector bundle, but it's a nice fiber bundle with affine fibers. This is a bond. So diff X is just the principal diff Kn bundle over X. You know, so yeah, but you know, and this is the fiber. So it's really the fibers are associated. So there is also, again, there is a, so this is a jet bundles, and there's a fiber-wise diff K yeah, I mean, sorry, I just use this diff k as a shorthand notation. J k right 1 1. So this is the diff k. So fiber-wise, diff k action on jk x. So what you can say is that you can take jk x mod diff k, and you can say that this is the object moduli. Wow. There's no terminology for this, but whatever we want. So this kind of, I really like calling this jet moduli space, and this one is just really, yeah, space. Over. So, and this is a central object in this strategy worked out by mainly the MyCU since the 1980s for the attacking these hyperbolicity questions. So, and in particular, the intersection theory of this object plays a central role in that strategy. So really the I would like to motivate this a little bit more. So so do you have any questions so far? Because these are the objects which we study. So in order to study intersection theory in this, at least in my world, we need some sort of compactification of that. So this jet moduli space JK1N mod diff k, this has a different compactification. So this diagram actually also came up in January in my talk. But so we have different compactifications, and they are actually leading to different applications in some sense in enumerative geometry applications and other applications. So this the first one is a certain component which we call the curvilinear component of the Hilbert scheme of k+1 points on Cn. So what is this? So this I denote by C Hilb k+1 Cn. This is actually, you take the actual curvilinear locus, so the set of curvilinear subschemes. So let's say, yeah, I mean, it's some local coordinates is really just the ideals where this quotient is isomorphic to the k+1 to the Morin algebra, the Cave-Morin algebra. So this is really basically what this is the set of, so what is this Hilbert scheme? The Hilbert scheme of points, k+1 points on Cn really parameterize ideals, or in other words, subschemes of length k+1. And this is a component of the puncture Hilbert scheme supported at some point. And in particular, actually, we can fix this to be the origin. Then, and that point, the type of this ideal, or type of is the local algebra that is isomorphic to this Morin algebra. So geometrically, this is the set of the set of points in the Hilbert scheme where the k+1 points on Cn collide and come together along a smooth jet, curved jet. So along a curve, and then you take the closure of that. So the component itself is the closure of that. So in the closure, there are many other types, of course, but this forms an open subset in that. So this is a singular, highly singular projective component, but it comes with a tautological bundles. So we have for any vector bundle V, there is a tautological bundle here Vk over the Hilbert scheme of, well, okay, and also here K Cn. And these tautological bundles actually encode several interesting animatic geometric questions over in classical animatic geometric questions, especially if you replace Cn by some manifold. And so this is important in animative geometry. Let's say curve counting. And also multi-singularity classes. Or higher dimensional Nakajima theory. So this is something I will not go in this direction. I just really want to indicate that there is this non-trivial, but what kind of very natural compactification. You can think of this as really like what is a curvilinear point on the Hilbert scheme is really just, as I said, these are subschemes supported on sitting on some k-jet of a curve. So that's actually here, but up to the reparametrization because you're only interested in the image of the curve. So that's an open part of that. And then taking the closure, this is a natural compactification. And there are known residue formulae for intersection theory of tautological intersection numbers on this component. Now the middle one, that's what actually I will talk about in these today and tomorrow. So there's another compactification which is you know what this course seminar series was about is the non-reductive g-adic motion. So for this we need to take some compactification. We just take the trivial compactification, and actually we'll have to blow it up in a proper way to get semi-stability equals stability, and then we can form this quotient. So this is what I would like to explain in details to how this works. So so we take starting with a projective space, we do some appropriate, very simple blow up to achieve semi-stability equals stability, and then take the quotient. So this is non-singular. And projective. And very nice intersection theory. Which roughly says that, I will explain in soon that, but this diff K is really a semi-direct product. It's a U-hat, so it's a semi-direct product of a unipotent radical and the C star. And calculating any intersection number, like proper intersection numbers, not everything, but basically works like we can reduce it to the integration over the quotient by C star sitting in diff K. So it's kind of, it's what we call classically the abelianization. So we can, there's this non-reductive abelianization theorem, which says that integrals over this U hat quotient can be rewritten as an intersection number over the reductive quotient, and that's in this case is a C star quotient because there's only one C star there. That's this diagonal C star, which it's not. So this is the main focus of this of today and tomorrow. And there is a very important, historically very important third compactification, which I call the Demai sample power. So this is really a, in this case, this is an iterated power of projective vibrations. Each of these is a projective bundle. Sorry, it's a projective bundle, and it's a super nice thing. So it's really it's non-singular projective. Captures. That's very interesting. It's important that it captures all. Sorry, my handwriting is all invariants in some sense, invariants. So captures all invariants. I will not explain this, what I mean by that. But the problem is that the integral formula, the intersection theory of this is also nice, right? Because it's just a power of projective bundles. But since it actually captures too many invariants in the sense that it becomes less efficient if you come to the some sort of tautological integral. So it's basically less efficient and not canonical. It's kind of with tautological. So I will explain what this is. Tautological integrals. These tautological integrals, which we really need in the hyperbolicity questions, and sort of tautological, some sort of tautological intersection numbers should be positive in order to get hyperbolicity of X. But it's less efficient. The formula is less efficient. So there is some technical reason for that, but which I will not go into. But really, I will focus on this non-reductive GIT quotient here. So yeah, this is now you can ask what's the relation between these different compactifications? Is there like they are all birational? Is there some sort of map between them? And actually there is a map. There is a resolution of this quotient. So let's say this is purely X case. So there is a resolution which with a morphism from this to that to the curvilinear Hilbert scheme. It's highly non-trivial to construct this resolution. There's a partial resolution, so it's not. Sorry, what I want, yeah, sure, yeah, not resolution. What I try to say is the undetermined loci for the there is a rational map from this to that, but it's not well defined. So yeah, it's not resolution of the singularity, but resolution of the undeterminacy. Locus of the. It's a really nice construction which actually uses heavily the GIT features actually this, and so we don't have to understand the full resolution of that locus, and in some sense this gives a real localization formula on the Hilbert scheme of points on manifold, on C-ends, or in manifolds in general. So in some sense, what this does is replaces one fixed point, which is a monomial ideal here, with several fixed points. And there's a formula, actually, you can add these up, which gives you the right contribution of that fixed point to the intersection number. And that's kind of, I like thinking about that as being, you know, the resolution of the problem with this being singular, and therefore there's no proper deformation theory and localization formula. So the tangent space are not right-dimensional and so on. But you can always, you can do this construction, and here it's an honest localization formula. So, but instead of having just one term for one fixed point here, you have several terms here. And this is actually encoded by a tree, a toric resolution tree. So anyway, this is just a comment, but it also can be used to get a new formula for these multisingularity and Thom polynomials here. So, okay. And it's less clear actually what happens with the tower. We've been trying to work a lot with Damian actually to get a similar picture from the tower to one of these, and it was it seems to be a little bit less clear picture. So yeah. Anyway, so this was the motivation part. And I would like to ask do you have any questions? Yeah, you have. So you can actually do equivariant localization. It's a nice picture. So it's a tower of bundles. So you can rewrite it as an iterated residue. So in the end of the day, the formula here and here is very similar. Here we have an iterated residue formula for these intersection numbers where we have k variables, whereas here, in some sense, this non-reductive geometric quotient does the quotienting by one step instead of k steps. So you only have two variables, as you will see. But you can actually, I wrote a paper about this it's a proceeding of elements paper, how you do the localization on that. And we kind of the hope that that gives you some sort of nice bound in the hypervelocity conjectures, but it turns out that you can't go below exponential bound there, whereas this one gives you polynomial bound. So. Right. Okay. So the goal here really is to explain how this integration works on this quotient. So yes. So we start with identifying the different elements of this formula, and so I will start with a reminder, of course, about this cohomology of non-reductive quotients. So in this setup, we have this U hat, which is diff K. This is actually a semi-direct product of the unipotent radical and a C star, and it's graded or positively graded. So so remember that U hat was this group where you have alpha 1 up to alpha k here, alpha 1 squared, alpha 1 to the k. So that's the diagonal part. This is your C star. And if you take alpha 1 equals 1, that's give you the U, the unipotent radical. So let's assume that this is a U hat act on some projective variety with respect to some ample line bundle over X. And so in this theory, we identify this Z min. This is the minimal weight space for the action. So this is by definition the set of points on X such that so yeah, so this means that X is really projective, so it sits in the so we have those points in X where the so X is fixed by this C star, and the weight of the dual or at this fixed point locus is minimal. So the weight space is really one-dimensional in this case. So you have some minimal weights and everything, and the fixed point locus for this. And this point is actually Z min. So there's the minimum weight space. So then we define this X min, that was the Bialy-Tubular stratum, is those points on X where the limit when t tends to 0 of e times X sits in Z min. In other words, those points in X where this coordinate, at least one of the coordinates corresponding to Z min is non-zero. So this action is, we have some, now we define this moment map. Sorry? Oh, yeah. T is in C star. Yeah. So we have a moment map. So really just very simple setup here. So is that, so so we have this X sitting in some projective space P of V, and we have an action, so G, which is in this case GL K, as a representation of to GL. Sorry, what I want to say is that it's a U hat, which is like my diff K group, as a representation to GLV. So it's a linear action. But the point is that we would like this to be in such a way that there is this S1, which is the maximum compact of C star. This is actually equal to the maximum compact in GL, so it's a U of V intersected by U hat. That's the maximum compact. And then how we define the moment map, this non-reductive moment map, is really simple, is that we have we restrict the moment map from P of V. So that's mu GL. So that's original. This moment map is actually to K is the maximum compact subgroup of the Lie algebra, dual of the Lie algebra, the maximum compact subgroup. This is actually, yeah, okay, I just say UN star, but that's actually sits in in GL star. And we restrict it to X. So then you get and compose by projection. So what we get in the end, so X, it's a map to GL star, and then we project it to U hat star. Oh, okay, I'll just say just Li of U hat star. So just remember that this one is this embedding is really this is the complex, this is the real dual of this maximum compact subgroup, and this is the complex dual, and then it's just the set of them. Yeah. So this is yes. So this is the home. This is the home. This is the real dual of UN, and this is the complex dual of GL. And really just this embedding, just take that, it sits in there because this actually then the image sits in the real part of that. Yes. Yeah, so that's a GL is equal to UN plus I times UN. This is just the complexification of that. And since, yeah, and then you just take I times the so it's a, yeah. So if you take the, so home R, U and R is basically the set of those in home C, G, and C such that phi UN sits in R. And you can automatically expand it as you can expect. But the point is that in this special case, this is the algebraic setup. This is what so this was the most natural thing you can actually do is that I mean, that's kind of the complex moment map here. You can restrict to X and compose it by the projection to the, and that's going to be a moment map in the sense how Francis explained. But for now, this is just for me, it's just a map, which I use to state the theorem. Yes. So what I fixed, yeah, it's going to be a product where you have a maximum compact subgroup, a pair of a maximum compact subgroup, and orbit of that, and a Kähler form, which is invariant under that maximum compact subgroup. And here I fixed it. So I really fixed it in the background. I fixed the Fubini because it's now in a project. So I can fix this to be the Fubini Studi matrix. So everything is with respect to the Fubini Studi. What? Sorry? Oh, but that's necessary for, you know, it's a more general setup where you have in the Kähler manifold and the submanifold, and you would like to define a moment map for an action on a submanifold such that it extends to the ambient. So for that is actually, there's no canonical choice there. But in fact, it's there's no, you don't gain anything actually in the algebraic setup if you work with that or this one. So that's kind of it. So there's, okay. So that's the setup. So we have that's a mu u hat. That's this non-reductive moment map. And so the theorem is the generalization of Francis's thesis. It's to me, this is the real evidence that this construction is canonical, because that was already a dream before, having a quotient where the integral formula has this form. So it's really just, you can reduce integration over the non-reductive quotient to the integration over the quotient by its reductive maximum in this reductive part. It certainly doesn't work for the other compactifications, only for this one. So this is a canonical construction. And this, I mean, in my view, I'm kind of doing this intersection theory for many years. This is kind of the main evidence for this to be a canonical construction. So the theorem is the following. This is just really repeating what Francis already explained, but this is a symplectic reduction, so non-reductive symplectic reduction. And it's highly non-trivial because the proof is way more involved and complicated than in the reductive case. But so we have the following statement. So this is the setup which we had before. So this is, you have your x and your action, and I only stated for u hat, so not in general, but this is for u hat. And of course, where stability was sub-instability. So so the theorem says that the zero level set of the u hat moment map sits in, and therefore also because it's a u hat invariant, so also the u hat sweep of that. So the u hat sweep of the zero level set sits in the stable locus for the u hat action. What was this? Just a reminder. So this was this x min, and we take away u hat times z min. U hat sweep of z min. That was the stable locus. And there's this, this is actually an open embedding. But it induces a surjective diffeomorphism. So, and that's kind of the reduction, symplectic reduction formula. Then, you know, when you have this, in the reductive world, you have this GIT stratification, which is really useful and helps in putting down the like calculating the homology and cohomology of these quotients. In this case, there is a stratification which is much simpler. So, and this is actually what I already put it here. So we have the stable locus and the u sweep of, or u hat sweep of z min. They cover this Bialystock stratum, and it's an equivariantly perfect stratification. So in particular, we can have a expression for the Poincare series, but what I will explain, and that's kind of the last three parts and the main parts from my point of view, right, at least for today and tomorrow, is that there is a non-reductive Shor-Martin picture. So I will explain in a second. But it implies the following thing. So we have a homology formula. So the everything is with rational coefficients. So x mod u hat is isomorphic to the quotient. So it's actually all about comparing it's kind of an abelianization thing. So this isomorphism actually let us compare the cohomology theory of the non-reductive quotient with the cohomology of the reductive quotient by the C star action. So it's x mod C star Q, but then you have to divide with the annihilator of E of, so the Euler class of U. I will explain in a second. So, so this one here is the so those elements here. So in such that annihilated by the Euler class of this V, which I will define. This is the bundle associated to the weights of the C star action on the Lie algebra of U. And we know that those are positive weights. This is positive grading. So this is the Euler class of that. Is 0. And also the intersection numbers. So, and that's kind of the ideal situation. So that's what the dream situation is, that if you have a want to integrate something on this on this projective smooth variety, the quotient of some form. So let's say alpha, that's equal to the just have to multiply with the weight. So that's kind of a dream situation. You just really want to, how would you do this kind of this quotient, like naively is really, this quotient is this quotient times naively the Lie algebra of U, and that's how we actually, so in some sense what this tells you is really actually topologically it says that the dual, the equivariant dual, or the dual of this quotient in this quotient is the Lie algebra of U, which is a super nice picture because that's what the ideal. So it of course never happens, well, not very often happens with compactifications, but this is a compactification where it, in some, or in other words, how you rephrase this, we can rephrase, and actually this is the Shor-Martin picture. I will explain in a second that this quotient and this quotient are very much related. This is actually really, this is cut out by a section of this bundle VU from the other one, and that's it. Yeah, okay. Let me explain this, because this is just really what I call the Shor-Martin diagram. This paper was never published in the end, and was born in Oxford, I guess, in 2000, and it meant to be an annals paper, but then it was never really, it never appeared. Yeah. I don't know if it's just a joke or. But that was a starting point of where we actually start. I emailed to Francis about this. Well, this should be true actually in the non-reductive case, because this picture is so simple, and maybe definitely follows from the symplectic reduction picture. So, and then that's actually started to work. So this diagram was the starting point of this work actually. So thanks to Sean Martin. Yeah. So the diagram actually, I just put it down for the, I just put down for the reductive case, non-reductive case, not the reductive case. So we only need basically just some part of the original diagram, but so we have the C star quotient, which is, we know that this is equal to, this is the reductive symplectic reduction mode S1, right? So you take the S1 moment map, the zero level set divided by S1, that's isomorphic to the GIT quotient by C star. And as I mentioned, there is this embedding, which is just X U hat, which is just mu 0 S1. So this I. And so it turns out that by the way, it has also fibers, but we don't use this part of the diagram. So if you have this setup that, yeah, okay, that's not important. In the U-hat case, it's not important. If you have some more general non-reductive, then it's actually interesting. But so this is just an embedding. As I said, there is a bundle over that. So there is a bundle over, this is what I noted by VU, which is actually the bundle over X mod C star. So let's define, so this is defined as mu S1 inverse 0 was S1 or C star, no, S1 of let's say of L, of U. So that's this U, this is the Lie algebra of, okay, let's say just Lie of U, right? So we know that there's a C star action which acts with positive weights on the Lie algebra of U, and this is just the associated bundle. And it turns out there is a section such that S inverse 0 is equal to, is isomorphic to X or is, yeah, mu U hat inverse 0. This one. So this part of the proof is the same. So it is not, it's really, everything goes through to this non-reductive case. This is one part of the shown part. In picture, the other part was actually with the other projection where the fiber-wise, we know that this, yeah, anyway. So and that implies this actually, right? So in order to take some intersection number here, we have the intersection here, we have the intersection number here times the Euler class. Okay, so yes, I think this is meant to be 1 hour, right? This talk. So I was, maybe I stop. Is that? Okay. So I haven't even started the details, but that's for tomorrow. So tomorrow the plan is now to use the formula which I put down actually at least. So if you reduce this to the integral over the C star quotient, there's the ordinary Jeffrey-Curwen formula for that. So you can rephrase and say that integral over X mod U hat of let's say it's not just an arbitrary alpha, but it's coming from the Curwen map. So it's an image of some equivariant class in X. And also it's enough to take the restriction of this equivariant form to the X min, because it's actually, I will explain it tomorrow. But if you have any form, because it's a surjective map, so any form can be written in this way. But there is an equivariant representative of that form, alpha. So that's going to be equal to some constant times the residue at z equals 0. And you take the integral over z mean of, well, you take the restriction of alpha to z mean. And that's going to be an equivariant form times the Euler class of Vu divided by the Euler class of the normal to z mean. And that's also an equivariant form, so it has one parameter z. So these are only this z is the equivariant homology. Is the generator of the equivariant homology ring of C star. So that is only a one parameter because we have only one C star here. So that's easy. So that's the formula, which seems to be and that's tomorrow we will identify all the ingredients here, and that's actually results this in this double residue formula in the end. So it's kind of not. It's not. I think the plan was originally just to explain this formula for in a very concrete example. This is my plan for tomorrow. Yeah. Okay, thank you very much. Yeah, absolutely. Yes, you're right. Yeah, yeah, sure. So, yeah, and also you can't just write alpha. You have yeah. Say again, sorry. In this case, it will be smooth. It's going to be a projective space. So what you do, actually, you take this compactification of JK1n. It's just a projective space, and then you perform one blow up at the point, and then we achieve semi-stability equal stability, and this Z mean is going to be a subspace of the exception divisor. It's kind of a very common picture, so normally that's what happens. But. And on that exception divisor, because it's a projective space, in this case, you can apply a second Jeffrey curve with the C star action. So that's where the second variable comes in. So this integral here is really, again, another Jeffrey curve, and then there is another residue variable W. And then you put together.